In the early 1990s, North Carolina's transportation network was a massive physical grid carrying millions of vehicles, but it was entirely disconnected. The Department of Transportation managed thousands of miles of roads, including 15,000 miles of unpaved dirt, using manual surveys and physical clipboards. The entire system ran on paper. Planning meant looking at physical maps and cross-referencing handwritten logs. To measure usage, engineers drove to specific routes and stretched temporary pneumatic tubes across the pavement. These tubes counted axles for a week, and from that tiny sample, planners extrapolated annual traffic averages. Those manual counts eventually made their way into TRADAS, a mainframe-era system running on HP UX servers. Data moved slowly, entered by hand, and processed in batches months after the actual traffic occurred. Managing mission-critical physical infrastructure based on delayed snapshots meant that as the state's population accelerated, engineers were forced to operate blind. They couldn't see the network. They could only see what it looked like 6 months ago. That delay became a liability as population growth surged. Compounding traffic volumes pushed the physical network to its absolute limit. Bridges built during this era carried enormous loads and endured decades of weather, but they were entirely passive. A bridge carried traffic, but it never reported its condition or warned of a structural failure. Planners tried to predict congestion using those old extrapolated averages, but the math no longer matched reality. A tiny sample of data from a Tuesday in March couldn't predict a massive bottleneck forming on a Friday in October. North Carolina reached a point where physical lanes alone couldn't solve congestion. Survival required integrating real-time information directly into the pavement and steel. The solution required turning physical concrete and asphalt into active, data-generating assets. Engineers retrofitted bridges with specialized sensors. Foil strain gauges on girders measure stress, while MEMS accelerometers capture vibration signatures. This high-frequency raw data flows continuously into local edge gateways, industrial devices running Linux attached directly to the bridge. Instead of sending every raw data point back to headquarters, gateways filter and compress telemetry locally. They package the critical insights and transmit them upstream using cellular networks or dedicated fiber optic lines. Traffic monitoring underwent a parallel upgrade. Planners replaced those old pneumatic tubes with radar units and computer vision cameras that capture speed, volume, and vehicle classification in real time. This continuous stream of raw intelligence turns the perimeter of the network into an active contributor to the state's operations. Millions of sensor readings per day create a secondary problem: ingestion. You need an enterprise-scale architecture to capture, store, and make sense of the telemetry. The state uses an advanced traffic management system to act as the central nervous system, pulling in live camera streams, weather feeds, and sensor data through streaming connectors. Behind the scenes, an enterprise Oracle database anchors the operation. It uses partition schemas to organize massive time series data. Oracle Spatial maps every physical asset geographically, while materialized views query this data to generate live dashboards for operators. This enterprise database stack became the primary tool for managing capacity. Instead of pouring more concrete, they optimized the concrete they already had. Continuous telemetry moves operations from forensic investigation to predictive modeling. With real-time ingestion, engineers detect structural stress as it happens, rather than waiting for a biannual inspection. Operators can see congestion forming blocks away and reroute traffic before it gridlocks. And this visibility is completely democratized. Small rural corridors and isolated towns now possess the exact same level of traffic analytics once reserved for the largest metropolitan hubs. The modern DOT acts as the administrator of a massive, statewide data ecosystem. Processing is now shifting from central servers back to the roadside, where traffic signals and sensors run local AI models to identify structural anomalies instantly. The physical bridge has become a thinking asset. It assesses its own health through sensors, transmits its status via telemetry, and logs its history into a database. North Carolina's transition from unpaved dirt to digital highways provides a clear blueprint for modernizing infrastructure. North Carolina's modern highways prove that the invisible stream of telemetry is what allows a state's physical footprint to think.